Hello everyone and welcome to today's webinar on ventilation strategies that work. I'm Richard Zücke-Schuller and I'm product manager here at Simscale. And in today's webinar, I'm going to be supported by two senior application engineers here at Simscale, Ajit Kumar and Darren Lynch. Ajit is mainly occupied with indoor thermal comfort studies and assessment at Simscale, while Darren is looking more at the outdoor environment, such as pedestrian comfort and wind loading studies in urban areas. So let's quickly have an overview on what today's webinar will be about and the different topics that we're gonna touch on today. We're gonna show you today mainly two case studies and what you can learn from these by using cloud simulation and how you can apply the technology to actually derive design insights and evaluate whether your ventilation strategy will actually work and also evaluate alternative strategies that might perform better. So first of all, we'll have a quick introduction for the people who are the first time here at Simscale to talk about what Simscale is and what we do. Then we give a short overview on the different applications in the architecture, engineering, and construction area that we can serve with Simscale. And then Ajit will take over to show you two case studies on indoor air quality and ventilation strategies done with Simscale, and a short live demo of our platform. And in the end, we'll have 5 to 10 minutes for a Q&A session where Darren and me will answer all your questions that might have come up during the presentation. And while I say that, please, whenever any questions come up during the presentation, feel free to use the questions functionality in GoToWebinar to post any of your questions. So in the end, we'll have some time to answer those. Okay, so first of all, what is Simscale and what do we do? So Simscale's mission actually is to bring high-fidelity engineering simulation to everyone that can benefit from it and make it actually technically and economically accessible. And we do that by using cloud-native technology. With Simscale, you can conduct simulations at basically any scale. So from single room ventilation analysis through outdoor microclimate analysis of basically a whole city. With Simscale's cloud-native technology, we enable you to simulate without any compromises. Instead of just analyzing a single design concept and a single operating point, you can go through a full sweep of different design iterations and operating conditions, all basically in parallel at the same time, without your local hardware being occupied at all, because you can access Simscale without installing any local tool. You just use it with your web browser, and all the heavy computations are done on the cloud. But computation power is not everything. So from the beginning, Simscale was designed with having a best-in-class UX in mind. So even without excessive training, you can be successful in running high-fidelity simulations on Simscale. And we do that with a variety of different solver technologies that we have integrated here at Simscale to use for every application the best solver technology. Now let's have a look at the different applications that we can actually do here. First of all, regarding the indoor environment, we see here a couple of examples that you could use Simscale for. So on the top left, we see a movie theater ventilation and thermal comfort assessment using Simscale. We can do single rooms, single classrooms, for example, as you can see on the top middle, but also large areas such as the top right restaurant thermal comfort study. On the lower middle side, you, for example, see a case study where we did a mixed ventilation analysis where we have analyzed the complete building performance in an environment where we combine outdoor and indoor simulation within one analysis. Now going on to the outdoor applications, here we see on the top row transient analysis that were done from a single neighborhood scale on the top left to basically full city scale on the top right. At Simscale, we use specific lattice Boltzmann solver called Pacefish, where we can run extremely large simulations in transient with a very robust technology behind, so you don't need to deal with all the nasty geometry cleanup that you're used to with traditional finite volume-based solvers, for example. And on the bottom, we see other examples where you can directly assess, for example, pedestrian wind comfort on an urban environment, or even do wind loading studies directly on Simscale. And now, after this overview, let me get back to Ajit for the presentation of the two case studies and have also a quick demo on the actual Simscale platform and interface.
Thank you very much, Richard, for the wonderful overview of who we are and how Simscale, as a cloud-native simulation tool, can help engineers and designers to make better design decisions. Apart from being here talking with us on the ventilation strategies, Richard is otherwise busy in designing product-related strategies within Simscale. So I remind everyone in the audience to make use of this opportunity, ask your product-related questions or feature-related questions on the messaging section of this webinar. Your questions will then be answered at the end of this session. Moving forward, we'll take a look at some of the case studies that explains the necessity of CFD for all these ventilation strategies. How important is CFD and what kind of insights are extracted from these analysis or simulations that can help better in sizing the HVAC equipments or even formalizing the ventilation strategy. For the past few years, Simscale's commitment to deliver a faster, accurate, and easy to use simulation tool has enabled our customers to leverage CFD to achieve meaningful design decisions on their ventilation projects. The next few slides will talk about two such case studies where design engineers have used CFD to improve and optimize their ventilation. Before jumping into the actual cases, a big shout out to two of our customers, Archetype and Greenlight, for providing us with these interesting case studies. The first one from Archetype involves assessing the heating and ventilation strategy of a classroom. What makes it interesting is that they wanted their classroom to comply with passive house regulations as well. Generally, passive house regulations are stricter with environmental and energy metrics. And this pushes engineers to assess their ventilation strategies at an earlier stage of their design process. Archetype started with an existing and verified layout for their classroom, and they used this verified design as a base case. The classroom model accounted for a variety of parameters such as U values for the roof, external wall and ground, the U values for windows, for different materials like glasses and frames. It also included radiation sources to represent solar gains. And we had about like 33 students and 3 staff as occupants. One other additional insight that Archetype wanted to get from this simulation is to find out the quality of the air. So the amount of carbon dioxide per occupant is also applied um, as about 400 particles per million. To check a little bit more about this case study, you can also take a look at www.simscale.com customers and then search for Archetype passive house. We'll see some of the highlights of this project and understand how CFD helped Archetype to overcome some of the challenges on this design. By taking a look at the base design, Archetype found two interesting issues that needs to be solved. The first one is due to the inlet. The classroom had an inlet which roughly drafted air on top of the occupants or the students sitting inside the classroom. This created in turn a significant amount of thermal comfort disturbances to the occupants. This was the first challenge that needs to be solved. And the next challenge was the existing air quality inside this classroom. The amounts of carbon dioxide levels were higher inside this classroom, and this needed to be addressed to make it a more efficient and whilst also minimizing the energy losses using the passive housing strategies. To achieve this, Archetype validated their cases. They ran different scenarios in parallel and then found out the optimal solution. For each of the configurations or the design variations, Archetype actually compared the temperature distribution within the space and also the air quality by means of concentrations of carbon dioxide inside the room. The first few configurations were done to find out which HVAC inlet configuration actually suits this classroom design. So as you can see on the left, the best and the optimized HVAC inlet was with a high wall diffuser utilizing the guide vanes, which actually pushes the inlet air to the ceiling and then the air actually hits the wall and circulates inside the room. This actually solved the first challenge where the occupants were getting a rough draft of air from the inlet. The next challenge was to improve the air quality inside the room. This was achieved by testing a combination of the high wall diffuser with various window openings. On the right side image you can actually see the HVAC inlet is set to the high wall opening, and additionally the window opening was included for better ventilation or better mixing of the air. The scenario 3, which is visualized here, had the best configuration where the air quality and comfort criteria were satisfied. Overall, Archetype was able to actually simulate different configurations in parallel using Simscale and found out the best scenario along with the window openings to make sure the passive house regulations were actually satisfied. This case clearly tells us the necessity of CFD to understand each and every specific case to improve our ventilation strategy. And the next case study is one of my favorites. It actually includes quite a variety of analysis and gives us specific inputs based on the external wind conditions that might affect the ventilation strategy. Before getting into the second case, I'll kindly ask our audience to write their questions in their messaging section so that we can answer your questions at the end of this section. Let's take a quick look at what we're going to involve in the next case. Now we have seen in the first case we were able to measure the indoor air quality and make few design changes and find out which is the optimal design for our ventilation. In the second case, we're going to add one additional component to the analysis, and this will actually bring us closer to what's happening in the reality. This study involves an apartment building, more of a student dormitory layout, and the main aim of this study is to find out a good ventilation strategy that works for all the rooms that are included in this layout. The evaluation of this particular case study will give us some interesting information on how the ventilation works or how the prevailing wind conditions can affect the thermal comfort or the indoor ventilation of this study. In the next slide, we can take a look at how we derived the internal conditions for this particular case. The first step is we took the model and then built up the surroundings for this particular building and analyzed that using the pedestrian wind comfort analysis within Simscale. This way, we were able to predict or extract the results for different wind directions. And for the internal case study, we'll be focusing mainly on one particular direction, which is the typical wind direction for this particular location. So in this case, we'll be focusing on the southwest direction and then see how this prevailing wind condition can affect the indoor ventilation of this case. For the internal ventilation studies, the third floor on the east wing of this building is considered. And the windows are supplied with the pressure measurements from the external wind conditions for the analysis that we did earlier. The doors are also considered with certain typical amount of leakage to mimic the reality. Just like the previous case study, we'll be taking one of the window open configurations as the base case and then compare that with different configurations that we want to conceptualize. While doing this analysis, we'll also take a step back and see or answer two of the major questions that every design engineer gets when starting a project. So we would like to actually see whether the natural ventilation is sufficient for this apartment, and during this process we'll also try to find out whether CFD can be helpful to decide a correct ventilation strategy for any kind of internal ventilation analysis. For this particular case, we'll be comparing the base design with different window opening angles or different configurations where the windows are opened with different degrees of opening. To measure the quality of the air, we'll also focus on the mean age of air within this layout and also consider a few interesting cases where the air changes per hour is also calculated. By doing these analysis, we'll be able to answer the initial couple of questions, but also these results can be extended to find out what kind of HVAC ducting or what kind of HVAC equipments are needed to satisfy the natural ventilation or the ventilation quality of this building. As you mentioned, we have the base case, which is on the left top corner of this slide, with a 10-degree window opening. So a constant 10-degree window opening is given on all the windows of this building, and the amount of air or the ventilation is actually studied using the velocity distribution. For comparison, we are going to measure or plot the velocity at 1.2 meters from the ground for all the cases, and this way we can compare how the opening of windows affect the internal ventilation. As you can clearly see, the base case has certain rooms where the ventilation is poor. For example, you can see these particular rooms in the second column, which are poorly ventilated. And by increasing the opening angle of the window, you can start to see some amount of one-sided ventilation happening and improving the ventilation of particular rooms here. The more you open the window, the more ventilation changes you can see inside these rooms. But after a certain point of time, no matter how much ever you open the window, there are no significant changes in the ventilation inside this building. You can pretty much see a pattern here. So the buildings or the rooms at the corner are well ventilated, and on the other side the kitchen is again well ventilated, but the rooms in the mid section are not ventilated enough. This can be even studied in detail by plotting the mean age of air in the next slide. The mean age of air plots gives us pretty much a good idea about where inside this building the air actually stays stagnant and where we have a good amount of ventilation. For example, if we take the base case with 10-degree window opening, the regions which are plotted with black color have good ventilation, or a constant amount of fresh air is being ventilated through these regions. On the other hand, where the region tends to be white or red, you can consider these regions where the air is pretty much stagnant and stays there for a long time before it is getting exchanged by the fresh air. And once again, the comparison between these different configurations shows us a good amount of insights on what is happening with the change in the window opening. Here the pattern remains the same. By increasing the window opening angle, you can see a good amount of improvement for some of the rooms here near the kitchen. But after a certain amount of opening, there are no significant changes in the mean age of air or the amount of fresh air that is brought into the system. For a good ventilation strategy, we need to consider each and every aspect of the prevailing wind conditions. As you can see here, one of the typical wind direction creates these significant changes with just changing the opening angle of the window. But what else can you get out of CFD that might help you devise a better ventilation strategy? The next slide is really important and gives you the exact need of CFD for these kind of analysis. Let's take a quick look at the results here. So for this comparison, we're going to focus mainly on the 20-degree window opening, and we're going to calculate the air changes per hour for certain rooms here. If you take a deeper look at this particular layout, there are two similar rooms on the top side of the apartment, where the volume of the room are pretty much same, but the amount of air that is coming or passing through this room are quite significantly different. This can be quantified if you take a look at the air changes per hour. So for example, the kitchen has an air change per hour of about 187. So this totally makes sense. The ventilation that is designed for this building is perfect for the kitchen, because for the kitchen we need a constant amount of fresh air coming in and going out in order to keep the smell and also the pollutants out of the room. There are certain regulations that we need to follow, but for this particular case you can see there is a huge difference between the air changes per hour for these two particular rooms. For room 6, it's at 4.81 air changes per hour, while the same volume room or a similar room has about 30 air changes per hour, just because of the prevailing wind conditions. CFD helps us understand why this is happening. Let's take a step back and see how the prevailing winds look like. And taking a look at the external wind study can give us a lot of insights about what's happening on this particular room. So if you take a deeper look at the bottom right corner, where we have the wind results from this particular direction, you can clearly see that there is a huge amount of air coming through and hitting this side of the building, and that's why we have a constant cross flow on the kitchen. And you can also notice something happening on the other side of the building, where the air actually passes through and then creates a recirculation zone exactly at this location. And if you consider a window at this location, you can pretty much imagine that the air is going to go through the window and recirculate out of the window if the other window is open. And this is exactly what is happening in this room 7. So you have a window where the recirculation zone starts and enters the room and then tries to actually escape, and this forms the single-sided ventilation for this room. This happens the same for the next room, which is room 8, where you can see the wind enters at one particular window and then tries to escape through the other window. But for the kitchen, you can see there is a direct flow which is coming from the southwest direction, and Thereby you have a high degree or a dominant cross flow which is entering this window and then going out of the other side. You can also pretty much see why these corner rooms are ventilated well enough. So on the back side of the building, the recirculation zone ends here, and the rest of the wind coming from the surrounding buildings or the disturbances that are coming from the surrounding buildings hits the corner of this building, and hence the air actually enters through this particular window and then rejoins this recirculation zone through the one-sided ventilation. On the other hand, if you take a look at the rooms which are not ventilated, the reason might be because this room lies in a region where the recirculation ends and also the interaction between the wind effects from the surrounding buildings start. So there is kind of a dead zone which is created in front of the building, and this might be the reason that there is not enough air that is coming through, or not even the one-sided ventilation is prevailing on this particular area of the room. Circling back to our initial questions, now with all these insights from the CFD analysis, we'll be able to answer if a natural ventilation is the right way to go for this particular building or we need forced ventilation. So for most of the cases where the window opening increases the ventilation in this building, but for the corridor and some of the rooms in this building, we definitely need an additional forced ventilation to satisfy the air changes per hour or to actually satisfy the air quality of this building. We have already seen the need for CFD for these kind of analysis to get or predict the natural ventilations better. And with all these results, you'll be able to make better design decisions on how to size your HVAC, and you can avoid oversizing or undersizing your HVAC equipments based on the prevailing wind conditions. Now that we have seen what kind of results can be extracted from the CFD analysis and how these results can help us design a better ventilation strategy. Up next, I will like to jump onto the platform and show you how these simulations can be easily set up within Simscale. For people who are taking a look at Simscale for the first time, Simscale is a cloud-native simulation tool. All you need is a simple browser and an internet connection to access the high-fidelity simulation. You can simply jump onto simscale.com, get into your dashboard, and then start simulating from that point on. We'll take a quick look at how these simulations are set up within Simscale, but any details in specific can be answered in the question and answer section. So just like any other CFD tool, the starting point of starting a simulation is to import a geometry. Simscale pretty much supports most of the CAD formats available in the market. You can simply drag and drop your geometry here. Once when a geometry is available, you can select the geometry that you want to simulate and hit the create simulation button. From here, you can choose the analysis type you want to proceed with. Simscale offers quite a variety of analysis type from which you can choose from, starting from a simple flow analysis to a conjugate heat transfer analysis, or even some of the mechanical or structural analysis. For this particular case, we will go for the convective heat transfer analysis. And by creating a simulation, you can already see a simulation tree created on the left side of your screen. From this point on, it is a simple top-down approach where you need to fulfill the red circles and then start the simulation. We'll take a quicker look at how the simulation looks like from the previous set of simulations that we ran. As I mentioned, we have the materials defined, we have the boundary conditions for particular set of windows applied here. We do have a pressure value which is extracted from the wind condition or the external wind analysis, and also the temperature conditions applied on each window here. Then start the simulations, which will give you a rough estimation of how much time the simulation is going to take and what are the computational resources. Once when you start the simulation, Since we're running everything on cloud, you don't have to wait for one simulation to finish. You can go ahead, modify the parameters, or even start multiple simulations at the same time. This way you can run a series of simulation at the same time and then start comparing the results. I don't want to get into details of all this simulation, but if you have specific questions or if you have any case that is similar to this one, please feel free to contact us either via the email or using the chat button on the Simscale platform. Let us know about what you want to simulate and we'll be happy to help you or assist you. Thank you all for listening. I'll now hand it over to my colleague Richard for the question and answers section.
Thank you, Ajit, for this great presentation of the different use cases. And it's really interesting to see how adding results of an external CFD simulation that takes into account the actual pressure distribution around the building by taking into account also the surrounding buildings has an actual effect on the indoor ventilation, and that we see that large differences between so similar rooms is really interesting. Now, just a little bit to conclude on what we've seen. So with CFD, you can definitely get a lot of insights that inform your design decisions for ventilation strategies. So you can get quantitative results that give you really the number values on the amount of air changes per hour, the mean edge of air in the room, ventilation efficiency, obviously temperature and air velocities within the room. But it also can give you CO2 concentrations, for example, and also you can do basically parametric studies of different conditions, for example, in inlet temperatures, inlet velocities, and so on. But as well, you can generate really qualitative results that show the airflow and the temperature distribution throughout the room through cutting planes, cut sections. You can do this for each of the different scenarios you want to analyze. And obviously, you can also do animations of these results and download these animations and communicate them with all the different stakeholders in the design process. So this makes it really an efficient tool to assess actually the ventilation performance, but also communicate these results understandably with other people that are involved in the design decision. So what we can see here, for example, on the left side is the visualization of velocity streamlines and is colored by the temperature within a room. And on the right side, we see an example how we can assess, for example, the distribution of a passive scalar. It could be, for example, a CO2 concentration within the room. And as another example, what we can see here is the temperature and velocity distribution at a horizontal slice through the room, that we can see how each individual occupant would feel with respect to temperature and the local airflow distribution around him. Obviously, besides the complete room analysis, you can also focus on different aspects of your ventilation strategy. So on the left side, what we can see here is an air conditioning unit from one of our customers, from Monotroth, where they analyzed the complete behavior of this air conditioning unit with Simscale. And not only the unit itself, but after analyzing and optimizing the internal efficiency of the air conditioning unit, they could also place it virtually inside a virtual classroom and then assess the effectiveness of the unit within an actual classroom design. And on the right side, it's an example of understanding the flow behaviors through different diffuser designs and how this might affect people that are standing or sitting directly below these type of inlets, and how this affects potentially their thermal comfort. Final example of a more complex air handling unit is what we can see here. So these air handling units are used in the ducting design, and with Simscale we can in detail analyze how the different components of these air handling units play together with each other. So we have the supply fan, we have other elements such as heating and cooling coils, we have filters, definitely something that is more interesting in these days due to the COVID pandemic. And we have guiding vanes to optimize the flow distribution and pressure loss within these ducts, and also louvers. So this is a very complex system, but on Simscale you can actually evaluate the whole system at once and how these different components affect each other, and then optimize either a single component of it or the whole assembly of them together, and then basically have the correlation whether under different conditions, such as different temperature conditions, different wind conditions outside, how this affects the performance of the air handling units for the ventilation strategy as well. And not only this, with Simscale, you not only can do CFD or flow analysis, but you can also do structural assessments. So, for example, investigate vibrations within these systems or within individual components of it. And then, with this being the last example, we have reached the Q&A session. And for this, I'd like to invite Darren to be part of this discussion. And maybe, Darren, let's see if we got already some questions from the audience that we could answer.
Hey, thanks, Richard. Can you hear me okay?
Yes.
Perfect. Yeah, so we've got quite a few questions coming, which is absolutely great. What I'm going to do is I'm going to start working through them. I'll start putting them out there, and then maybe if it's nice and easy, I'll answer it. Maybe Richard, if it's slightly harder, you can answer it. And of course, we'll both jump in if either of us miss anything.
Yeah, please,
so the first question I think we come to.
Questions for me, sorry.
The first question we're coming to. How accurate are these simulations? Is there a study that compares a simulation versus reality? So firstly, we do absolutely have a validation page in our documentation section. And in this validation page, we've got many different validations that help us understand how, for example, pressure coefficients compare to wind tunnel studies, or also how indoor ventilation studies compare to tests. So absolutely check that out, see if you find anything relevant. And of course, feel free to reach out to us if you need any information, any more information on that. Is there anything to add there, Richard?
No, I think that's the best resource to start. If you don't find your example there, you can directly reach out to us and see if you can have maybe some unpublished studies that where we can share the results individually.
Absolutely. Great. So the next one is, does the study have to be done for different wind directions? So I would actually advise, yes, it would be wise to take a few scenarios that you know would be the most dominant type wind flows and assess each of those for natural ventilation. So in this case, we had one very clear dominant wind direction, which of course we used along with a typical summer wind speed. But you could of course take calm hours and assess the wind direction and the wind speeds on each of those scenarios. And really, in the end, this is going to build you up a much better picture of what the natural ventilation is going to be like for different times of the year, different strategies, different scenarios, to help you understand the ventilation strategy better. Once again, Richard, anything to add to that?
No, it was perfect. One thing maybe to add, you could also do, for example, a study on the outdoor analysis, for example, for 36 or 16 wind directions, and then put the pressure coefficient results into a different analysis software, kind of, for example, as building energy modeling tools, where you can then assess for the full year the typical behavior for each hour of the year in a faster way, maybe not as accurate as resolving fully the internal flow, but then you could go back from the results of this simulation and pick again the worst case scenarios, and then do a detailed study back on Simscale for resolving locally the conditions, the CFD.
Absolutely. Great. So the next question is the tool to transfer the pressure coefficients, CP, from the outside model to the inside model programmed by the user? So maybe that's probably best for me, since I set up the original simulation. So at the moment, what we're doing is we're doing this kind of programmatically, kind of manually. So there's a halfway house that we're at. What we actually do is we set off the outdoors wind comfort simulation. This creates our pressure coefficient values for us. We programmatically download those pressure results, process them into pressure coefficients. That we then do some additional upscaling depending on the scenario that we're doing, and we input that manually into the indoors study. But of course, as we've covered in the past quite a lot, that we have got the API, all of this could be programmatically done and automated, so that you don't have to do this manual process over and over again. Actually, that is a great use case for our API there. So although this particular simulation wasn't set up using that, it's absolutely a workflow that you could employ. Does that answer it sufficiently?
Yeah, definitely. Nothing to add.
Excellent. Yeah, and also whilst I'm asking these questions, feel free to just type in any additional questions that you might have. Absolutely no problem at all. So I think we covered that question already. The velocity in the kitchen is so much higher than the other rooms. Are the doors of the other rooms closed? I think that's quite an important question. So a fundamental understanding of this project, yes, the wind going straight through the kitchen is unrestricted, completely unrestricted. The flow that would be going through one room into the corridor and out the other side is restricted by the doors. The doors are modelled as closed with a very small leakage applied to it. So that's why we're not getting the vast through flows that we would expect if the doors were open. And of course, if you wanted to model the doors open, that's absolutely something you could try. You could just you could change the pressure drops across the doors to model a open door, and that would be the scenario there with all of the room doors open as well. Excellent. I think the last question here is how would this be useful for identifying mitigation alternatives to counter stack effect in tall buildings? Richard, do you want to have a crack at that, and then I can add after?
That's a good question. Not really sure how this is definitely related to the stack effect, but maybe Darren, you have a better stab at this?
Really, to mitigating counter stack effects in tall buildings, what we would really identify this as helping to do would be to better visualize the flows, identifying the flow paths within the building. And this is really going to help us understand what about the the building's construction is allowing this draft to go through, countering the stack effect. So we're really going to be identifying high pressures. We could identify high pressure facades on the outside. That would be, of course, a easy inlet for the flow, and low pressures as the outlets. When we feed this into the indoors simulation, we're going to use that information to help identify where flows are moving through stairwells, where flows are moving through elevator shafts to counter this stack effect. So it's really the extra information that we can use towards mitigating these scenarios that can really help us here.
Great answer. Thanks, Darren.
No problem. Feel free to add on to that if you need to. The other questions we have are how are users applying Simscale for COVID mitigation? Once again, maybe for you, Richard.
Yeah, I guess there are a few key concepts, right, for COVID mitigation, which we maybe all have meanwhile learned, right? It's all about air exchange rate and reducing regions within the classrooms where we have long standing air. Right, so, and this is exactly what you can do with Simscale, what we've seen before. So we can efficiently analyze and assess air exchange rates, mean age of air within the rooms, and use this information to actually find different types of ventilation options that provide a higher air exchange rate under different circumstances, and basically also remove locally the areas where we have stagnant air, and also increase the air exchanges locally, which you would need a CFD tool for to really resolve the local effects of the placement of the inlets and outlets of the ventilation system, and together with maybe occupants and other obfuscations for the different flow paths through the room.
Excellent, thanks, Richard. So we're still getting questions coming in, which is absolutely great. Keep them coming. We can, if we don't get time to answer them, we will of course follow up with the answers. So absolutely no worries on time. Just ask your questions, and we'll do our best to answer. So I've got another question. How were the opening angles of the windows modelled? So I think that's maybe I'll answer that one. So when we wrote this script to take the pressure coefficients from the external flow analysis to the indoor flow analysis, what we also did is we used a calculation that was provided by a UK government site. I think the original source was in a spreadsheet form that we obviously implemented into code. And this gives us a relationship of window size, window opening angle, and to pressure drop and flow rate. And that is what we implemented in Simscale. When we get this relationship between pressure drop and flow rate automatically from our code, this is what we actually use to model that that restriction, if you like, of the windows. I hope that answers your question. Okay, feel free to ask any follow-up questions, as I said before. Richard, maybe I'll pass one to you. Does this software accept temperatures from the user being from 10 degrees, seeing the simulation and then seeing what happens to a 30 degrees uplift?
Don't know if I understand the question correctly. Could you repeat, or could you maybe formulate it in a way that?
Yeah, I'm struggling to understand it as well. So maybe, Will, if you could ask it again, maybe a simpler form for us, apologies, and we'll absolutely have a stab at the question. No problem at all. Can you calculate flow rates through windows, Richard?
Yes, obviously you can do that. So the core results that you get from CFD are temperature and velocities, right? And with the POS processor, for example, what you could do is compute bulk calculator values that compute the average velocity, the integral of certain quantities over surfaces. So you can pick the surfaces in the POS processor and will integrate the values for you, or for example, compute the average velocity and also flow rates.
Perfect. In which case, I think we're there. If anyone's got any more questions, or you're typing a question, just raise your hand. We can hang on the line. Or alternatively, if you don't have any other questions, then we'll wait a minute and then we'll call it a day.
Yes, while we're waiting on the last questions coming in that we might answer later, maybe that's a good point to remind you about further webinars and where you can look for them. So just here, visit webinars and workshops at Simscale. You can have a look at past webinars and rewatch them, or also sign up for new upcoming ones and learn more about Simscale applications, insights that we've got. And yeah. Final thing, if you you can directly get into contact with us as well if you have follow-up questions on the webinar. If you want to know more details about the tool, if it applies to your use cases, how how you can get started, and so on, reach out to sales@simscale.com or visit the website and sign up, and we'll get back to you and arrange a meeting where you can maybe explain your use case, and then we see how this could be solved on Simscale. So before we finish, Darren, is there any update on the question or any more that we can answer within the last minute?
No, I think it still looks like we've answered everything. So, of course, if you've got any follow-up questions, then feel free to reach out on the email addresses mentioned in the slide. But otherwise, thank you very much for listening, everyone.
Great. Thank you, Darren, for your great answers. And also Ajit for the awesome presentation of the use cases and of the platform. And thank you for joining the webinar today. And yeah, as said, reach out to us whenever you need more information, and we're happy to see how we can help you with your application on Simscale. And see you again for the next webinar. Until then, have a great time.